In this question, we have two identical metal balls, each with a mass of 0.25 grams, are suspended on threads. Okay, there's a lot of information in this question, so I'm going to annotate it as I go. So the mass is 0.25 grams for each ball. Okay, the balls have identical charges and remain in equilibrium, so that means the forces on them are balanced, as shown in the diagram. The length of the thread is 3 meters, so it's already annotated on the diagram there, and each string makes an angle of 7 degrees with the vertical. Find the distance between the two charged balls x. So I'm measuring the distance from the center of one to the center of the other. Okay, this is just a geometry question. So we're going to look at this triangle like this. Is a right angle triangle. So if I draw it down like this, you can see we've got the hypotenuse, which is 0.30 meters. And what we want is the opposite on the other side there. So you can use sine. The sine of 7 degrees is opposite over hypotenuse. So if I would do 0.3 times sine 7, I get 0.3656 meters. But that's actually only halfway from the center of one ball to the center of the other. So we need to multiply that by 2. So our actual distance from center of one to the center of the other is 0.07312 meters. Okay, part B, calculate the charge on each ball. Okay, so here we're going to have to use the fact that the forces on each ball is balanced. So I'm going to look at the ball on the right here and look at the force on it. I'm going to draw this onto the diagram. So we know one of the forces acting on it is going to be the weight, okay, mg. Another force acting on it is going to be tension, which acts along the string. And to balance this force, there needs to be a third force, because you can see there's a component of the tension towards the left. So there's going to be a force towards the right as well. And that comes from the repulsion from the other charge ball. Because they both have identical charges, they're going to repel each other. They might both be positive or they might both be negative. It doesn't matter. They'll repel each other like this. Okay, so we need to balance these forces. To balance these forces, the best way to do this is break it down to horizontal and vertical components. So you see this tension, we can break that down. T cosine theta. So T cosine 7 is the upward component there, and T sine 7 is the component towards the left like this. So the first equation, let's start off by balancing vertical forces. So the weight, mg, just acting downwards, is balanced by the upward force, which is T cosine 7. Now, I know all these numbers, actually, I can actually work out the tension T. So T is going to equal mg, which is 0.75 times 10 to the minus 3, so turn the grams into kilograms. That's the standard unit for mass, times 9.81, which is G, divided by cosine 7 degrees, making sure your calculators are degree mode right now. Okay, that gives you the tension along the string there. Okay, so now let's start off balancing the horizontal forces. So T sine 7 is acting towards the left. The force on towards the right is the electric force there. Now the electric force comes from the repulsion between these two balls, these two charged balls. So that means we can use Coulomb's law, Q1, Q2 over 4 pi epsilon r squared. Now because the charges are identical on both the balls, we can have Q squared instead. Okay, I'm going to rearrange this and make Q the subject because charge is what I'm trying to find. So if I get T sine 7, and I already have T, so I'll put that in a minute. 4 times pi times epsilon naught, which is from your data sheet, it's a constant, times r squared. Okay, so let's put these numbers in. We do have r squared, by the way, which is the distance from the center of one to the center of the other. We calculate that in part A. So square root of the tension, which I just calculated, 2.47 times 10 to the minus 3 newtons, times sine 7, making sure that's in degree mode, 4 pi epsilon naught is 8.85 times 10 to the power minus 12 from your data sheets. And the distance between them, which is r squared, is the one that we calculate in part A using trigonometry. And that squared gives us a charge of 1.3 times the minus 8 coulombs. Okay, example 2 now is very similar. I'm going to enter the information as I go through this. A ball of mass 0.12 kilogram is suspended by a thread between two parallel plates. So that parallel plates means that we're actually in a uniform field right now. So not a radial field like we had before between those two charges. So we won't use Coulomb's law. We'll use the equation for uniform electric fields. Okay, so the parallel plates are separated by a distance of 10 centimeters. And the potential difference between the plates is 1,000 volts. Okay, and when the ball is given a charge of plus 21 microcoulombs, it comes to a rest as shown in diagram. Okay, so if we say it's coming to a rest, then we're gonna have to assume that it's coming to equilibrium as well. So it's not only comes to a rest, but the forces are balanced. And the angle between the vertical is theta, so that we can try to find the angle theta here. Okay, so first step is to draw a free body diagram. So mg is the weight downwards, tension along the string, and an electric force towards the right, like this. So we can resolve the tension again, just like how we did in the previous example, and we're going to balance these forces. Okay, so let's start off with finding the electric force on the charged ball there. And we can do that by finding the electric field strength between these two plates, which is a uniform field. So we'll use potential difference divided by the distance between the plates to find the electric field strength. And then when you multiply that by the charge, you get the electric force, like so. So the potential difference is 1000 volts divided by the distance, which is 0.1 meters. Okay, that's in meters now from centimeters, times that by the charge, which is 21 microcoulombs, and that gives us the force, 0.21 newtons. And that's going to balance the horizontal component of the tension, the force towards the left from the string there. So P sine theta. Okay, we can't solve this because there are two unknowns, P and theta, so we'll come back to this. So let's start off by doing vertical forces. We've got vertical forces mg, and we've got all the numbers to solve this. We've got the weight, the mass, which is 0.12, and times that by 9.81. So we've got the weight, and that's going to equal the upward component of tension. So that's t cosine theta. Okay, so now when you have equations like this, t sine theta and t cosine theta, a common trick is to do the top equation divided by the bottom equation. Now, why am I doing this? Well, this is because I know of a mathematical identity which you learned in math. Sine theta divided by cosine theta equals tan theta. So if I divide these two equations, let me write it like this. So we've got the first equation on the top there and the bottom equation on the bottom there. And the t's will cancel out. And so the number on the left of we simplify, and we can do that by putting that in the calculator. The t's cancel out, and sine theta divided by cosine theta becomes tan theta. So to get theta, we just do tan inverse of 0.178. And that gives us an angle of 10 degrees, which is reasonable.